Hello, good morning everyone. Welcome to Guru Brahma classes for JEE and NEET. We are in the chapter Ionic Equilibrium, and in this session we are going to learn about ionization of a weak acid. What is that? Ionization of a weak acid or dissociation of a weak acid. Let's start the session, right? Let us see here. Ionization of acid and base and the degree of ionization we are speaking about. Generally, how do you represent an acid? Okay, if there is hydrogen with electronegative element, and those are called as what? Hydra acids. What are those? Hydra acids. Hydra acid. What is meant by hydra acid? Which contain electronegative element along with the hydrogen. For example, HCl. What does this contain? Electronegative element along with hydrogen. These are called as hydra acids. Next, oxy acids. What are oxy acids? Let us take H2SO4 is oxy acid. What is oxy acid or oxo acids? Oxy acid means which contain electronegative element. Here, what is electronegative element? Sulfur is the electronegative element. Along with the electronegative element, if both hydrogen and oxygen are present, that is called as what? Oxy acid. Along with electronegative element, if the acid contains hydrogen and oxygen also. In hydra acids, we don't find oxygen. Whereas in oxy acids, we find oxygen along with electronegative element and hydrogen. Okay. Here, let us see. Protonic acid. We are speaking about what? Protonic acid. What is meant by protonic acid? See here. Acids which donate protons are generally known as protonic acid. So what is proton? What is proton? Say, what is proton? Proton is represented as hydrogen, H plus. Proton is represented as H plus. Right? If the acid donates proton, if it has to donate proton, it should contain proton. Okay. See, these hydra acids and oxy acids contain protons. Okay. So these hydra acids, oxy acids, as they contain proton, and those acids containing proton and which can donate proton or which can release proton in a solvent, then those are called as what? Protonic acids. What are those called as? Protonic acids. So these are represented as HX. Hydra acids are represented as HX. Oxy acids contain electronegative element, oxygen and hydrogen. See, for example, HCl, when dissolved in water, they release water, H plus Cl minus. Is it able to donate proton? Yes. See here represented HX hydra acid. When dissolved in water solvent, it releases H plus and X minus. Okay, they are releasing this H plus. They can donate this H plus. What is H plus called as? Proton. In the same way, like protonic acids, if you go with some other examples like protonic acids, H2SO4, HNO3, H3PO4, all of these are oxy acids, and they can donate proton, so they are protonic acids, etc. Understood? So when these protonic acids are dissolved in solvent, especially water, the best universal solvent, okay, they release protons. Okay, they ionize into H plus and X minus. What are these hydra acids? For example, HCl. Already we have seen in water releases H plus Cl minus. In the same way, HBr in water releases H plus Br minus. In the same way, H2SO4 in water solvent gives 2H plus SO4 minus 2. In this way, the acids in a particular solvent, if they release protons, they are called as protonic acids. Okay. Next, base. Let us come to base. The compound which contain OH minus ions are generally, according to Arrhenius, we say, according to Arrhenius theory, we say the compound which contain OH minus are generally, not always, generally. There are some many exceptions. Okay, generally known as what? Base, and is represented by as BOH. Example, let us take example NaOH, like KOH. Okay, barium hydroxide, cesium hydroxide, lithium hydroxide. In this way, there are many bases. According to Levy's theory, according to Arrhenius theory, it is said that compound which is having OH and which is able to release OH minus ions in water, that's called as what? Base. So for general condition we are speaking about. So when the base is dissolved in a particular solvent, then it releases B plus and OH minus. Like for example, let us go with NaOH, and dissolved in water gives you Na plus and OH minus, like KOH. Okay, K plus OH minus. Magnesium hydroxide. Okay, dissolved in water. These are all when they are dissolved in a particular solvent. Then what do you get? Mg plus 2 plus 2OH minus. Okay. Here the extent of ionization, see, they are ionizing. Ionize into B plus and OH minus. This is all what process? This is the process of ionization. Why we are calling it as ionization? Because they are producing ions. When they are dissolved in a particular solvent, they are releasing ions. So that process is called as what? Ionization. Okay. When they are ionizing 100%, see 100%, then they are called as strong. They come under strong electrolytes, strong acids, strong bases. So when do we say that they are strong electrolytes? That means strong acids or strong bases. We say that when their alpha is equal to 1. What is that? When alpha. What is alpha? It is also called as extent of ionization or degree of ionization is equal to 1. Then they are strong. Strong electrolytes. That means strong acids and strong bases. Okay. Here it is given in the form of alpha percentage. So the same can be represented in the form of alpha percentage. What is alpha percentage? alpha into 100 is called as alpha percentage. So now if it is 1, 1 into 100 gives you what? 100 percentage. Okay. So when degree of dissociation is equal to 1 or degree of dissociation percentage is equal to 100 percentage, what does that mean? How many molecules you dissolve in water? All the molecules of that electrolyte are completely ionized. They are 100% ionized. Okay. So what is the formula of alpha? Alpha is number of moles of electrolyte ionized or dissociated by total number of moles taken. Total number of moles. Okay. So for example, if 2 moles are dissolved in water, among those 2 moles, if all the moles, how many moles you have dissolved in water? 2 moles. All the 2 moles are dissolved in water. Then what will be alpha? Alpha will be equal to 1. How many moles you are dissolving in water? If all the moles are dissolved in water, then alpha is equal to 1. Alpha percentage will be equal to alpha into 100, that is equal to 1 into 100, that is equal to 100 percentage. Are you getting this? Right? So strong electrolyte, how you differentiate strong electrolyte and weak electrolyte? Simply saying that if alpha is equal to 1, that means if it is completely dissociating, we say that it is strong electrolyte. If it is not dissociating completely, if alpha is not equal to 1, here we consider it as a not strong electrolyte. It is not strong electrolyte. So it can be considered to be weak electrolyte. Okay, so the extent of ionization is less for weak acids and weak bases. So for weak acids and weak bases, we say that what is that? Alpha is less than 1. Alpha is less than 1. It can be whatever it is. It is less than 1. It is not dissociating completely. It can be 0.3, 0.2, 0.1, 0.001. So differentiating strong electrolyte and weak electrolyte, strong electrolyte alpha is equal to 1, whereas weak electrolyte alpha is not equal to 1. It is less than 1. It is less than 1. Okay. So let us see. So we are speaking about this Ostwald dilution law. Ostwald dilution law. What does this law say? See, Ostwald applied law of mass action. In chemical equilibrium, we have studied law of mass action, where it describes the relation between rate and the concentration of the reactants. How does rate of a reaction depends upon concentration of the reactants? So Ostwald applied law of mass action upon whom ionic equilibrium. What is ionic equilibrium? The equilibrium which involves ions. Okay, in chemical equilibrium we have studied, we did not study about the equilibrium involving ions. Especially in ionic equilibrium, we study equilibrium involving ions. So that's called as what? Ionic equilibrium. To verify whether equilibrium really exists or not. So he applied law of mass action for what? For whom? Ionic equilibrium. To know what? Whether the equilibrium really exists or not. Later, what did he find? That the constancy of equilibrium constant. So equilibrium constant is remaining constant for the dissociation, ionization equilibrium of whom? Weak electrolytes. For weak electrolyte, K is remaining constant. What did he find? For weak electrolytes. For weak electrolytes. Okay, he found that for weak electrolytes, K is K. What is K? Equilibrium constant. What is K? Equilibrium constant. Is remaining constant. Okay. From that he found that, he observed that, confirmed that equilibrium really exists. And for weak electrolytes especially, for example, let us take weak electrolyte CH3COOH. What is this? This is called as acetic acid, weak electrolyte. Whenever we are mentioning this weak electrolyte, which is not dissociating completely, whose alpha is less than 1, then compulsorily we have to write forward arrow and backward arrow, because in the case of ionization of weak electrolyte, there will be equilibrium existing between dissociated ions and undissociated molecule. So whenever we are representing a weak electrolyte, you have to remember that there will be an equilibrium existed between dissociated ions and undissociated molecule. Okay. But let us see, before we have discussed HCl and dissociation. Did we write, for example, let us see here, let me mention HCl. I have mentioned HCl. Am I writing forward and backward arrow, both arrows? No. Why? Because it is a strong electrolyte. What is that? It is strong electrolyte. It dissociates completely. It happens only in one direction, forward direction. NaOH I have mentioned, it is strong electrolyte. Strong electrolyte means Na plus and OH minus. Only one direction. But when it is weak electrolyte, okay, there will be equilibrium existing. Equilibrium can be obtained only in the case of reversible reactions, not irreversible reactions. That means whenever we find a weak electrolyte, we have to see that both forward and backward reaction occurs and an equilibrium exists after a certain time. Okay, so let us see. In the case of strong electrolyte, the equilibrium constant does not come to be constant, indicating thereby that strong electrolyte remains completely ionized. See, strong electrolyte remains completely ionized. Hence, there is no question of equilibrium. So, for strong electrolyte, there is no question for equilibrium because K is not remained constant. So, for a weak electrolyte, see, consider a weak binary electrolyte. Binary electrolyte means which contain two ions having concentration C and degree of dissociation alpha. Okay. So he has considered a weak electrolyte AB. Okay. Weak electrolyte means there will be equilibrium existing between dissociated ions and undissociated molecule. Okay. Let alpha be degree of dissociation. Okay, which we have seen. And let C be the at time 0, that means reaction has not started. Let C be the concentration of AB, binary electrolyte, binary weak electrolyte. C is the concentration of AB at time 0 time, that means reaction has not yet started. Okay, that means there will be no A plus and no B minus. at time t is equal to equilibrium, let C alpha be dissociated or ionized. How much AB has been ionized? It is C alpha. This type of questions, this pattern of questions, this type of explanation we have seen in chemical equilibrium. How does this C alpha comes? Okay, and we know that when 1 mole of AB is dissociated, 1 mole of A and 1 mole of B is formed, B minus is formed. When C alpha is ionized, here how much A plus will be formed as C alpha and B minus formed as C alpha. Initially there is C concentration AB, and how much is ionized? C alpha is ionized. Then the remaining concentration of AB at equilibrium will be C minus C alpha. C minus C alpha. Then how can you write equilibrium constant for this? We write equilibrium constant. Okay. So what we write? K equilibrium is equal to product of the product concentration by reactant concentration. Then that is equal to. So what are these concentrations? Already we have studied that these are the concentrations of reactant and product at equilibrium concentrations. What are those concentrations? Equilibrium concentrations. Concentration of A is C alpha and the concentration of B minus is C alpha by AB will be C minus C alpha. Then if you write this C square alpha square by C into 1 minus alpha. C gets cancelled. Then K equilibrium can be written as what? C alpha square 1 minus alpha. Okay, so this is the formula. Okay, to calculate what equilibrium constant for a weak electrolyte. Which electrolyte? Weak electrolyte. So if the electrolyte is very weak, if the electrolyte or acid is very weak, very weak represents that alpha is very much less than 1, or even less than 0.1 also. Okay, so then what you can write? 1 minus alpha will be almost equal to 1. So in the case of very weak electrolyte, what you write? K equilibrium is equal to C into alpha square by 1 minus alpha is 1. Here only we have seen. So simply I can write that K equilibrium is equal to C alpha square. Okay. And I can write from this alpha square is equal to K equilibrium, right, by C. And alpha is equal to root K equilibrium by C. Understood? Alpha is equal to root K equilibrium by C. So this is how we calculate alpha, right? Then we have studied that at equilibrium, see, at the equilibrium, concentration of A plus, we have seen that it is C alpha. Concentration of B minus is also C alpha. Then what is C alpha? Okay, so which is equal to C into alpha. Now we have derived C into root K equilibrium by C. This can be written as root C into root C. C can be written as root C into root K equilibrium by C. So root C cancel. Then what you get is what? Root C into root K equilibrium. Then I can write it as root K equilibrium into C. Okay, so this is all what? This is all according to Ostwald dilution law. Okay, so this was proposed. So that was here what you are finding completely. So concentration of A plus or concentration of B minus both are same, which is equal to C alpha, and that C alpha is equal to root K equilibrium into C. Understood? So based on this Ostwald dilution law, we go with the, or we study about the ionization or dissociation of a weak electrolyte. Ionization or dissociation of a weak electrolyte. Let us see that. So limitation, Ostwald dilution law limitation, this is only for weak electrolyte. It is applicable only for weak electrolytes and not for strong electrolytes, because strong electrolytes are dissociating completely. Okay, so this law is not applicable for strong electrolyte because strong electrolytes are almost completely ionized at all dilution. This is all important. So how much water you take, that means how much you dilute with, whether you dilute with less water or whether you dilute with more water, the strong electrolyte is found to be completely ionized and hence do not give accurate results. Okay, so for a weak electrolyte, this is for a weak, the process of ionization. The process of ionization is an equilibrium process for whom? This is for weak electrolyte. That means weak acid or weak base. Okay, weak acid or weak base. So let us see acid. What is this? Acid, which is weak acid. In the case of weak acid, already we have seen, we cannot write single arrow. We are writing both forward arrow and backward arrow. What does this represent? This represents that it is weak. And we write equilibrium constant, and that equilibrium constant here it is called as what? Ka, and that is called as what? Dissociation constant of acid. Because this is acid, as acid is dissociating, we call it as a dissociation constant of an acid. Okay, so why we are writing equilibrium constant or dissociation constant of an acid here? Because it is weak acid, and in weak acid there will be equilibrium existing because it is a reversible reaction. Okay, in the same way, if you see the dissociation constant of base or base ionization constant. So what is this? Weak base. In the case of weak base, there is equilibrium existing between dissociated ions of base and undissociated base. So we write equilibrium constant, and that equilibrium constant is called as a dissociation constant of a base. What is Kb called as? Kb called as a dissociation constant of a base. Dissociation constant of a base. Understood? So this is applicable for whom? Only for weak electrolytes. It is not applicable for strong electrolytes, because strong electrolytes completely dissociates, completely ionizes. Okay. So let us see in the case of a pH determination of weak acid. We are speaking about a weak acid. In the case of pH determination of weak acids, let us see how we can find the pH of a weak acid. Let us, weak acids do not dissociate completely in water. Their percentage degree of dissociation is very less. Let us take CH3COOH. The same process Already we have seen that process. Let us see once again. So we are applying what law here? Ostwald dilution law. Why we are applying Ostwald dilution law? Because that can be applied for weak electrolytes like weak acids and weak bases. That is what we are seeing here. Let us take what acetic acid CH3COOH. As it is weak, there is both forward direction reaction and backward direction reaction. CH3COO minus plus H plus. Okay, let what is that? Let alpha be degree of dissociation. Let alpha be degree of dissociation. Okay, and initially when the reaction is not yet started, the concentration of acetic acid is C. The concentration of acetate ion and H plus ion is 0 because it is not yet dissolved. It is not yet ionized. That means at time t is equal to 0. When it is dissolved in water, that means both forward direction reaction and backward direction reaction occurs, and only some of acetic acid will dissociate into acetate ions and H plus ions. How much it dissociates? Let it dissociates C alpha. Before we have seen already. Okay, how much it has been dissociated? C alpha. Originally, how much is present? C. Then at equilibrium, if C alpha is dissociated, how much remains? C minus C alpha. Okay. And already we know that when 1 mole of acetic acid dissociates, 1 mole of acetate ion and 1 mole of H plus forms. If C alpha is equal to 1, that means 1 is dissociating, 1 and 1 are formed. If C alpha is equated to 1, then here how many acetate ions are formed? C alpha. How many H plus ions are formed again? C alpha. Then if you write equilibrium constant for this reversible reaction, which is at equilibrium, then equilibrium constant K equilibrium, now it is called as what? Ka, dissociation constant of an acid. Now only we have seen for weak acid equilibrium constant, we mention it as dissociation constant of an acid, that is equal to CH3COO minus concentration into H plus ion concentration by CH3COOH concentration. So what are these concentrations? Concentrations at equilibrium, and that is equal to C alpha into C alpha by C minus C alpha, okay, which is equal to C square alpha square by, okay, C into 1 minus alpha, CC gets cancelled. This is all we have seen before also. So Ka can be written as C alpha square by 1 minus alpha. So this is the formula to calculate Ka. Okay. Then if the acid is very weak, what is that? Very weak. That means its alpha is very much less than 1 or very much less than 1. What does that represent? 1 minus alpha will be almost equal to 1. If 1 minus alpha is equal to 1, I can write for a very weak electrolyte, then I can write a very weak acid, Ka is equal to C alpha square. But I can write Ka is equal to C alpha square, because C alpha square by 1 minus alpha gives you 1, divided 1 by 1 gives you C alpha square. So Ka is equal to C alpha square. If I want alpha is equal to root Ka by C. This already we have seen. Root Ka by C. Then what will be concentration of CH3COO minus at equilibrium, that is equal to C alpha. And what is the concentration of H plus ion concentration at equilibrium? That is also C alpha. Then what I can write? Okay, what will be C alpha? C alpha is equal to C into alpha. Already we have it. What is that alpha? Root Ka by C. Then I can write it as root Ka by C, that is equal to root C. So C can be written as root C into root Ka by C. So root C gets cancelled. Then C into Ka, that is equal to root Ka into C. So H plus ion concentration, or which is also equal to CH3CO minus concentration. So whether it is state ion concentration or H plus ion concentration, and that is given as what? Root Ka into C. Root Ka into C. Okay. So this is application of what? Ostwald dilution law for whom? For weak electrolyte. So you can all find this. See, H plus ion concentration is equal to root Ka into C. So for calculating the pH of weak acid, first all we calculate from the equation. So this is the complete equation. This is the complete equation. If alpha comes out to be very much less than 1, it is even less than 0.1, then 1 minus alpha will be taken as 1, and we use the formula Ka is equal to C alpha square. And otherwise, if alpha is not very much less than 1, then compulsorily what we have to take? We have to take the complete formula. And what is that? Ka is equal to C alpha square by 1 minus alpha. Understood? Right? Then let us see the next part. So now we have seen that H plus ion concentration. What did we see? H plus ion concentration. H plus ion concentration is equal to root Ka into C. This we have seen. Okay. Now we are calculating pH of a weak acid. Calculating pH of a weak acid, we know that pH is equal to minus log H plus ion concentration. So we have only H plus, we don't have minus log H plus. Then what we can write? Let us multiply on both sides with log. Log H plus is equal to log Ka into C power 1 by 2. So root Ka into C can be written as Ka into C power 1 by 2. Okay. Now we know that log A into B. What is that? Log A into B is equal to log A plus log B. This way you can write. Okay. And log A power x is equal to what you can write? X log A. These two things we know. Right? Here log, this can also be written as, let us, log A power x. Then I write it as half into log Ka into C. Okay. Then half log A into B is equal to log A plus log B. Like log Ka into C is equal to log Ka plus log C. Understood? So this is what all log H plus ion concentration. Log H plus ion concentration. If I multiply with what minus on both sides, then what I get? Minus log H plus ion concentration is equal to minus half log Ka plus log C. So this can be written as minus half into minus log Ka minus log C. Okay, what did I do? Minus is here, so I can get it as minus log Ka, and minus into plus gives you minus. And we can write that pKa can be written as minus log K. Can I write? We have studied that pH is equal to minus log H plus N concentration. In the same way, I can write it as minus log Ka is equal to pKa. So what I can write now? Half minus log Ka is equal to pKa minus log C. So minus log H plus ion concentration is equal to pH. Minus log H plus ion concentration is equal to pH. So what is the formula to calculate the pH of a weak acid whose Ka and concentration is given? When Ka or pKa is given for a weak acid and concentration is given, then we can calculate pH of that weak acid by this formula. Or if you multiply half on both sides, then what you get? Half pKa minus half log C multiplying. Okay, hope so you are understanding this. So this is the formula to calculate what pH of a weak acid. pH of a weak acid. So for any weak acid, these are the formulas. This we have derived. Ka is equal to C alpha square. We have derived this. Then alpha is equal to root Ka by C. We have derived this. H plus ion concentration is equal to C alpha. We derived this. So C alpha can be written as root Ka into C. And now we have derived what is the pH of a weak acid. pH of weak acid is equal to half pKa minus half log C. Okay, so where alpha is degree of dissociation or ionization of acid, where C is molar concentration of the acid, and Ka is ionization constant of acid or dissociation constant of an acid. So each and every single step, each and every single point I mentioned in this lecture. So you go through each and every single point. Okay. If any student or if anyone feels it is faster, you play the video with slow speed. If any student feels that this video is slow, then you can play the video with some more speed. So this is a video, because you can play as you like, right? That is the fetching of this video. Hope so you understood each and every point which is discussed here. In this session, what we have discussed about the ionization of a weak acid. In the next session, we shall solve some problems on this ionization of the weak acid. Thanks for watching. We shall meet in the next class with the next new topic, right? Thank you.